it moved. Okay, so let me recall what we have been doing. So we introduced what is called quantum probability space. A quantum probability space is just a tuple like this, A, phi, where A is contained in M and C, is a unital. That means it contains identity star algebra. Okay. That means it contains identity. 1 is in A and X is in A, implies X star is in A. That's what star algebra means. Star is the adjoint and it's an algebra. Okay. And phi is a state. Phi is a function from A to C, which satisfies this following. Phi is linear. Okay. Phi of 1 is 1 and phi of X star X is greater than 0 for all X in A. And that's all. Okay, it's a, and phi is this is positivity condition. Phi of X star X is greater than 0 is positivity condition. And we proved the following. We proved if A equal to M and C, okay, then any phi is actually given by a what is called a density operator. Okay, any phi from A to C, I mean any phi, a state, is given by a rho in M and C satisfying the following condition: rho greater than or equal to 0 and trace of rho equal to 1, and it satisfies, and phi of any A equal to trace of A rho. Okay. This is for all. So we proved this. This is how any state will look when A equal to M and C. So these things we proved last time. So then we introduce what are called events. So I will move. Okay. So events. So this is the analog of quantum probability space. This phi is like a probability measure. Okay, the probability, whatever the probability function, and the probability space is replaced by this. Earlier we replaced by algebra of function, which is replaced by an subalgebra of M and C. So events, I'm just recalling for 5 minutes. Events are in the classical case, events are sets. Here the events are all those. So events, let's say events of A, okay, events of A is equal to all those P in A such that P square equal to P star equal to P. Okay. All those, these are all projections. These are all the events. Then we have seen that if some, I was using E and F, I think. So let me use that. If you have E and F, two projections in E of A and EF commutes, then we say they are compatible, FE. Okay. Then the distributive law holds. So I have to say what is distributive law. Distributive law holds. What it means is on E we can define, on E of A, on the set of all events, we can define operations. So if we have E, F in E of A, then we can define E sup of E and F, which is just the projection onto the span. I mean, if it is Hilbert space or something later when we talk, we have to take the closure. Here we are assuming it's all finite dimension, okay, which is just the span of E and F. You take the subspace generated by the, span of range of E and range of F. I should say range of E and range of F. Projection onto the span of range of E and range of F. They are subspaces, and you take the subspace generated by those two subspaces, and it's a projection onto that. So that is E of E. And E, this inf is something, it is just the intersection. Okay, this is just the projection onto range of E, intersection range of F. Okay, this is like intersection, that is like union. Okay, so then in general, if E and F commutes, okay, if EF equal to FE, then I should say that EF1, F2, they commute. I mean, there are three projections. If F, E1, E2 mutually commutes, they all commutes with each other. Then F1, this is like union E2 equal to F1. So this is what is called distributive. Distributivity. I find it more difficult to write it in the iPad than writing on the board or something. Okay. Okay. So in general, distributivity is not true. There is something more. If you have a probability measure, I mean, if you have, of course, if E1 and E2, if E1, I mean, we say E1 and E2, I mean, in set theory, E1 and E2 are two sets are disjoint if their intersection is empty. Similarly, if E1 is orthogonal to E2, then of course they will commute. Then phi of E1, E2, which is just the union, is phi of, I mean, they commute then, phi of E1 plus phi of E2. Because E1, this E2 is nothing but E1 plus E2, okay? And they are orthogonal projections. They don't intersect, okay? They are in a different subspaces. Then the projection up to the subspace generator is just the direct sum. Okay, we will see all these things for a general Hilbert space anyway. But if you know about, I mean, I think you know in finite dimensional cases. So then E1, the sup of E1 and E2, the union, the correct whatever the projection union in the language of projection, which is E1 plus E2. So then since phi is linear, which is equal to phi of E1 plus phi of E2. Okay. So
phi is a state.
Phi is a state. Yeah, I'm just saying everything for a state. You have a fixed quantum probability space, an algebra and a state. And then if you have two events, E1, E2, which are disjoint, in the sense they are orthogonal projection. I mean, disjoint means here it's not that. I mean, you have to. This is not disjoint. If you have something, you have a subspace like this. You have a subspace like this. Their intersection is trivial. Every subspace will have zero. Okay, so the intersection is trivial, but they are not disjoint. But only the x-axis and y-axis, they are orthogonal. Okay, by disjoint we mean orthogonal projections. Okay, so when they are orthogonal to each other, then it is additive. That's what we call as disjoint here. Okay, in this projection language. So, but in general, in classical probability, I mean, I don't want to revoke all the notation. In classical probability, the following thing is true. If you have any sets A1 and A2, I mean, in the earlier notation, in whatever we call as the sigma algebra, I mean, you can just say, take any subset, okay? You don't need to worry about sigma algebra here because it's finite set. Okay, the omega is finite, sample space is finite. Then A1, I mean, it is actually true that A1 union P of A1 union A2 is less than or equal to P of A1 plus P of A2. Okay. In fact, it is true that P of A1 union A2 is equal to P of A1 plus P of A2 minus P of A1 intersection A2. Okay, the intersection part is missing, so it's less than or equal to this. When they are disjoint set, this is equal. This is not true in quantum probability unless they are compatible. Okay, when they are not compatible, when they don't commute, this is not true. So I want to give an example. I want to give a counter example, a proposition. Okay. So first, if E1 sup E2, okay, is I have to say what is less than or equal to E1 plus E2, okay, as operators. Okay, then I will write here. I mean, all these things I'm less than or equal to positivity. I'm going to recall it again straight for general Hilbert space, but this is just for matrices. Okay, so I will just write it informally below. Okay, so when even the sup is less than or equal to even E2, then wait. Yeah, this is okay. Then E1, E2 equal to E2, E1. Then they commute. If this is true, then they commute. Okay, so this is what I want to prove.
So what does it mean?
Yeah, I'm going to say.
Even
that's what I'm going to say. That's what I'm going to say. So we have an operator A is set positive. Definition. This is definition. You can take this to be the definition. Okay. A is positive if xi A xi is greater than or equal to 0 for all xi in the vector space. Okay, Cn or whatever. A is in ML. Okay. And we say A is greater than B as matrices or operators if A minus B is greater than or equal to 0. That's all. Okay. A minus B should be positive by whatever the inner product. We have the definition through inner product. Xi is greater than or equal to 0. Okay. I mean, usually when the inner product is linear in the first variable, complex linear in the second variable, we usually write A xi. Okay. Here I'm writing xi. Okay. Sometime by mistake I may put the A before, but you should correct me and if I don't remember. Okay. So this is what it means by something greater than that. Okay. So now the proof. So I have given the meaning of what it means by something is greater than that. So suppose if I want to prove that if E1 sup E2 is less than or equal to E1 plus E2, it makes sense. E1 is an operator, E2 is an operator. You can sum up two operators and this is less than this. Okay. Suppose E1 sup E2 is less than or equal to E1 plus E2. This just means, I mean, I can bring it one of them, E1, E2. This is a projection, but the minus E1 is less than or equal to E2. Okay. So this means E2 minus this is this. Now, if you apply E2 on both sides, this simply means, see, if you have, I mean, this just says that this operator, see, this is something you verify this, okay? I will do it later, but when this is just finite dimension, this just means E2 on E1, this will be clear, okay? E1 is equal to E1, E2. See, both these things sits inside this E2, then this commutes. Okay, this is true. Okay. Now, if you hit E2 by E1 sup E2, you will get the smaller one. If you have a bigger projection, you hit it by a smaller projection, you will get the smaller projection. Okay. So this implies E2 minus E2 E1 equal to E2 minus E1 E2. So this which just implies E2 E1 equal to E1 E2. So I have given an exercise, which is a simple exercise. It should be clear later anyway. So you do this for finite dimension. It's better you try this. Okay. Okay. So that's all. So if the sup is less than or equal to, as operators, less than or equal to E1 plus E2, then E1 and E2 has to commute. That's what this says. Okay. So now I come to the counter example. Okay. So you tell me if you want to read something because the screen is so small. I just multiplied. No, that is an exercise. It's an exercise. Okay. Just try that. Okay. That is because it is less than E2. See, it is like everything sits inside the space E2.
Yeah.
Okay. These are all operators in E2. E2 is like an identity on that.
Yeah.
Okay. So identity,
so
you can come. So you just get convinced about it. It is like they sit inside E2 as an operator. So if you hit it by E2 on both sides, it's the same thing.
Sir, from the first line, how do you come to the second line?
This one, I just
from the exercise first line after that.
If I just multiply, I mean, what do you mean by that? Oh, this E2, this is just E2 E1. E2 multiply, I mean, the E1 sup E2 is a bigger projection. When you hit a bigger projection by a smaller projection, you get a smaller projection. Okay, that is a bigger projection.
So, by projection, I can imagine that by this definition of projection.
I mean, it's the same thing. You just write down the definition. Okay, what is a projection? So, see, that's what I'm saying. We will do. That's what you should do. If you have a projection P, what does it mean? P x equal to x if x is in the range of P. Okay, P x equal to 0 if x is in the orthogonal complement of P. Okay, so anything can be written as x plus x, maybe x perp. You put x perp. Okay, any vector can be written as x plus x perp. Okay, we will define projection for a general Hilbert space and we will go through all these things. Okay, so if you have an idea, you go write down these things. Okay. Okay. So, but you must have seen these things in linear algebra. Haven't you seen these things? I don't know what is done in linear algebra. Okay. But orthogonal, all these things. So if you, so anything corresponds to a, you can replay, I mean, you can forget about the projection, you can think about the big, the range of projection, which is the vector space. Okay. So if you have a bigger projection, you hit it by the smaller projection, the bigger projection, smaller projection will have an orthogonal complement in the bigger projection that will get killed. So you will get only the smaller projection. Okay. That's all. So once, I mean, these things you write down the definition, everything. You can mathematically rigorously write all these things. Okay. So it's better you practice that. Okay. So this is now I give the counter example proposition. Okay. There exists a state. And so we will equivalently call a state as a function from an algebra to C, but when the algebra is Mn, we call the density function as a state, or I call it, say it's a density function. Okay, state or density. I mean, it's equivalent thing. Some people call that a state. Okay, in some of the literature, the state is actually called as a vector in the Hilbert space. I mean, vector in the Cn or something. Okay, that means then you get the, I mean, if you have a vector xi in Cn, then you have this operator, okay, which has trace 1, it's positive and all that. Then there is a state corresponding, there is a functional corresponding to this. Okay, so that is, and you know, we know this state, no? A going to, we all first define this, A going to xi. Okay, so some people, in some place literature, any vector in Cn is called as a state. Okay, that corresponds to this function. Okay, all these things are equivalent things. Okay.
So but a state can be a combination of functions of that form, right?
Combination of what?
Like psi1 projection onto psi1, projection onto psi2. That could be a state. Like
Projection onto xi1.
the span of psi1 and psi2.
Sure, but it should have trace 1. No, span of that will be another vector. What do you mean by that? It should be unit vector.
Yeah.
So you can take span of, I mean, you can take different things. That will be another vector.
Another vector.
Yeah. I mean, if it is not, sometimes it's not given by a vector, it's given by a pure operator. Okay. So that is what is called mixed state. Okay. If it can be given, I mean, if you can take span and if it gives rise to another vector, then it is again a pure vector, pure state. Okay. There exists a density matrix or a state, equivalently a state, okay, such that, so the state is trace rho, density matrix rho in MNC, okay, such that, and projections E1, E2 in MNC, okay, projection E1, E2 in MNC, such that trace of rho E1, yeah, I think this is the one, E2, is less than or equal to, is not valid. Okay, that's what I want to say. Trace of rho E1 plus trace of rho E2. I mean, this is the probability of E1. Okay, this trace rho E1 is the probability of getting E1. This is the probability of getting E2. That is the probability of getting E1 sub E2. Okay, that is supposed to be less than this thing according to classical probability, which is not true. Okay, does not hold. Okay. This is not true. Okay, so we have already proved. So there exist projections E1, E2, such that E1, E2 less than or equal to E1, E2 does not hold. For that, I just write it like this. Okay, I just trace it. This does not hold. Okay, this, what does this mean? This means that E1 plus E2 minus E1 sub E2 is not greater than or equal to. So this means that is E1 plus E2 minus E1 E2. This is not true. Okay, that's what it means. So what does it mean? This is positive means if you apply on any xi, that should be greater than 0. There exists xi where this is not true. So there exists a xi in Cn, and I mean if you have one xi, then you can divide it by its norm and you get that norm xi equal to 1. There is a unit vector xi such that E1 plus E2 xi this is greater than, this is not true. Okay. Yeah, like E1. Yeah, this is, I'm just directly writing it. Okay. E1, E2. Okay, this is not true. There exists a xi like this. Now take rho equal to this. Take rho equal to the, I mean, given by that vector, which I have already said. This is a one-dimensional projection onto that. This is just a projection onto that side. Okay, this is this. Then it's clear. Then then the trace rho is precisely that. Okay, trace A rho is actually xi A xi. Okay, and it does not satisfy. And it does not satisfy. Satisfy. I don't want to write it. This whatever you call it a star or something. It does not satisfy the star. Okay. I called that equation a star. Okay, and I just written it does not satisfy star. So this, I mean, this is additive, but it's what is called subadditivity is not true. Additivity is true because when it is disjoint means they commute. So additivity will be there. So when they are not commuting, this is not true. Okay, it's only true only when it is commuting. Okay, so this is about events. So is there anything more about events? Okay, nothing. So let's go to what is called a random variable. Random variable or observable. Okay. Random variable, or it's also called observable. Okay. In classical probability space, a random variable is just a real valued function from omega. Okay, so it's just a function, and that those functions in the algebra, and you can see that any such function can be written as in classical case. Classical case, and a random variable or observable f is equal to summation. I mean, it's just a finite thing. So 1 AA, it can be written like this. Okay, we just replace it with projection. Okay, in quantum case, a random variable is a self-adjoint operator. Operator x in A. Okay, that is x equal to x star. X equal to x star. So if it is a self-adjoint, I mean, if x is a self-adjoint, x equal to x star, then spectral theorem. Okay. Then theorem says there exist projections EI, okay, I equal to 1 to k or something. I mean, this dimension may be n, they may be in M and C, this I equal to 1 to k is less than n, such that x equal to summation lambda I EI. Okay, I equal to 1 to k, where lambda i's are real numbers. If you have a self-adjoint operator, then it can be diagonalized with respect to something. And this lambda 1, lambda 2, these are all the eigenvalues. And this one, the EAs are the eigenvectors. Okay, lambda 1 to lambda k, eigenvalues. X and E1 to EK are the eigen spaces or eigen projections. I mean, projections equivalent to spaces, so I'm calling it as eigen spaces or eigenvectors. Okay, so this is the same thing. Okay, Now, if you have a random variable x with eigenvector definition, quantum random variable is just a self-adjoint operator in the algebra. That's all. That's what I have said. A random variable is a self-adjoint operator. X equal to x star. Okay. Then spectral theorem tells you that can be, you compute the eigenvalues. You can compute the eigenvalues, and you can compute the eigenspaces by using whatever the technique you know. Then it can be written as x can be precisely written like this: summation lambda I. Yeah, it will be diagonal with respect. I mean, usually your matrices will be defined with respect to some orthonormal basis. Okay, here it will be with respect to some other orthonormal basis. So you will there will be a unitary playing that role.
Yeah, the eigen
spaces, eigenspaces. Okay, where it is constant. On EI, x is just constant lambda I. Xi equal to lambda I xi on EI. That is that's the definition of eigenvector, no? These are all collection of eigenvectors. EI is the collection of eigenvectors. EI is a projection. It's a collection of eigenvectors with eigenvalue lambda I. That is EI. Okay, that's all. Okay. So any random variable can be written like this. Okay. Now all these E1 up to En, the EI, EJ commute. Okay. What do you have? EI, EJ commutes, not just they commute. They are equal to 0. EI, EJ equal, they are orthogonal to each other. Okay. If I not equal to J. If I not equal to J, they are orthogonal projection. The product is 0. Okay. So the probability, I mean, so now if you have a random variable, the quantum random variable, it is like a function taking values, n by k values, lambda 1 up to lambda k. Now the probability of the random variable xi equal to lambda I. You can take any other value in a lambda, but if it is not in lambda I, it's 0. Well, maybe you can say the random variable is taking values in real line. Lambda equal to 0 if lambda is not in the set. Okay, lambda k. And probability of xi equal to lambda, sorry, not xi, sorry, xxx. There is no xi, I'm sorry. That is just x. We don't have an xi. Is equal to, it is just trace. I mean, we have a, see, I have defined random variable, we have a state behind, okay, which is equal to state of rho EI. Okay, or phi of EI if you want, okay, which is equal to phi of EI. I mean, this is when you have when the probability space is MNC, okay, or maybe we can just write it as phi itself. I mean, you can write it rho, but that is when it is in MNC. That will be the case most of the time. G is equal to phi of EI. Okay. So the random variable takes the value lambda I. Okay, lambda I with probability phi of EI, and then summation of EI equal to the identity operator, and trace of 1 is 1. Okay, I mean the phi of 1 is 1. Okay, I use this notation 1. Okay, 1. So summation phi EI equal to 1. So you get a probability measure. So we get a probability measure. So the random variable. So the quantum random variable. Do you know how to avoid this? Why is this keyboard popping up all the time? I don't know. Touch something and see, I don't do anything. It's popping up all the time.
I think you can't start with
Huh?
we are not supposed to.
I didn't do anything, but I have to put my hand on that, no, to write it. Okay, so the quantum random variable random variable x, that is just a self-adjoint operator x, okay, gives rise to a probability distribution. Distribution on its eigenvalues. Which is just lambda 1 up to lambda k or whatever. Okay. With P of P, I mean, distribution means you for each, you have a set of n elements, probability of each element you should know, and probability of this lambda 1 is lambda 1, which is just P of lambda 1 is equal to that phi of ei, whatever. Okay. So one single random variable is like a classical probability space. Okay. I mean, in quantum probability, there is no confusion. If you have one single random variable, it is like just the classical random variable. So the self-adjoint operator has an eigenvalues, lambda 1 up to lambda n, lambda k or whatever. Okay. And you have the state and you have the eigenspaces. You take the phi of ei or trace of rho ei, whatever. Then that gives you numbers, k numbers, and probability of that x equal to lambda I is precisely that, given by that. Okay? Which is, so you get a classical distribution, classical probability distribution on the set of eigenvalues whenever we have a random variable in a state. Okay. So only when we have two random variables, then there's a problem. Okay, you can tackle two random variables in the classical case together, but that is not possible here. Okay, the problem is, one problem is non-commutative, then there is something called uncertainty principle. I will come to that later. Maybe in the next class I will come to that.
Could you just repeat this?
Last shall I do it in the board? I have written it here.
Yeah.
Okay. Just see, you have, what do you have? You have a, see, you have a this. This is a quantum probability space, right? This is a quantum. You have a state A and phi, and a x in A, x equal to x star. This is what is a random variable. That's all. Okay. When, I mean, this is anyway a self-adjoint operator in M and C. Okay, so x will look like this. Summation lambda I EA. Lambda is our eigenvalues, and this is equal to this. Okay. Now, so this x takes the value lambda I on this EI. Okay. So x takes the value lambda I means that is the probability of x equal to lambda I. X is lambda I on EI, right? It is just a constant. On EI means what? If I is in range of EI, x I is nothing but lambda I. This is eigenspace, it is eigenvalues, right? Okay. So it takes the value lambda I, it is constant lambda I. Okay, constant lambda I. So the probability of, so we just call it, you can call it probability of x equal to lambda I equal to probability of that, the quantum probability of that, which is P of A. Okay. So you get a distribution x equal to lambda I, x taking the value lambda 1, lambda 2 up to lambda k. You have phi of E1, phi of E2 up to phi of n. You get n numbers. Okay, which determines the probability distribution on this finite set, which is just a classical probability. You have this is omega equal to lambda 1 up to lambda n. Okay, and anything can be given by p1 up to pn, right? So you get a classical distribution on that.
So are we applying the spectral theorem for any star algebra?
No, spectral theorem is true for any self-adjoint operator. What do you mean by any star algebra? You know, our A is contained in M and C. We are not using any abstract algebra. Our A is anyway in M and C. Okay, so any self-adjoint operator will be summation lambda EI. Whether our algebra is whole of M and C or not, that doesn't matter. Okay. See, if it is whole of M and C, every state is actually given by density operator or something. Otherwise, also it will be given by something, but which you can compute. But it depends on the algebra. You have to compute its dual, how the dual looks, and all those things. Dual space. Okay.
But the eigenspaces are not in our eigenspaces will always be.
Eigenspace will be in the algebra.
Will always be.
It will be in the algebra. I will give you a proof later. I'll get. I mean, if you have a x is in that is your confusion. That's a good question. Okay, if x is in EI, if you have a self-adjoint operator, then the eigenspace is in that. The projection will be in that. Okay. Why is that true? Immediately. Okay, I will prove something called double commutative theorem. The next class, it will be I will prove it something. Maybe in this class I will not have time. I think I already started late, so it will be clear from that. Okay. Okay, it will be clear that all those projections. That's a good question. Okay. Of course, if you work with MNC, all these things are clear. If you work with the A, you have this question. Good. Okay, yeah. So then only you can define phi of EA. Correct. So your phi is defined on A. So only when EAs are in A, you can define that. So EAs will be in A. Okay. So I will prove it later. Okay. So if X is in A, okay, X equal to X star, then X equal to summation lambda I EI, and EIs are also in A. Okay. EI is a projection. So that's what I will prove it later. Okay. Okay. So now if you are given a self-adjoint operator, you get a probability distribution on its eigenspaces. Okay. So now you can talk about, so once you have some numbers, lambda 1 up to lambda n, and you have a probability distribution, you can talk about expectation, variance, and all those things, like you do it in the classical thing. So that's what you can do. So expectation of X equal to expectation of that probability distribution. A probability distribution, generally a probability measure is some numbers 1 up to n or something. But usually by a distribution or something, it will take values on a real line or something. You will have particular value, lambda 1 up to lambda n. So you can talk about the expectation. Okay. So the expectation E of a random variable X, okay, equal to summation lambda I probability of X equal to lambda I, right? Which is just summation lambda I phi of EI, which is equal to, which is just phi of X, that's all. Okay. If you want, when A equal to M and C, then this EX is nothing but trace of some X row. Okay. Where rho is, phi is given by that row. Okay. Rho is a density matrix. Okay. Okay. And variance also you can define. Variance of X. How is variance of X is defined? That is expectation of this random variable X minus EX. EX is a number. Okay. X is a self-adjoint operator. So if you add two self-adjoint operator, that is again self-adjoint operator. So X minus EX is also a self-adjoint operator. Okay. And its square is also a self-adjoint operator. You can square a self-adjoint operator. It is just square. It will have the same eigenspaces, except that the eigenvalues will be squared. You can see if you have a random, if you have, I will write it here. I will erase it. If you have any something, summation lambda I EI, if you have any random variable like this, then you can talk about f of X, where f is a function from lambda 1 up to lambda n to C or whatever. Okay. Then f of X is nothing like f of lambda I EI. You can talk about f of anything. If you have a function on the eigenspace, okay, then you can talk about f of X. By f of X, we mean this. Okay. So you can square, you can do this, you can do all these things. You can subtract the expectation, which is just a number. You have a random variable X, then you have expectation X, which is just a number. Then X minus EX is a self-adjoint operator, okay, which has the same eigenspace. Okay. Then you can take the square of it. Okay. So in classical thing, if you have studied some statistics, which will be this is same as E of X square minus EX whole square, right? Which will be true here also. Okay. This is exercise. You just square it and apply all those things, you will get it. Okay. So that is also true. So this is the variance. And this is exactly equal to phi of phi of, which is just phi of x minus ex, right? Square. So which is equal to phi of x square minus phi of x whole square, which are just number. Okay. And when it is M and C or something, you have to use the rho. Okay. Is equal, so when A equal to M and C, when the phi is actually given by a density matrix, this is equal to trace of rho x square, which is just a number, then trace rho x whole square. Okay. And it is given by a density matrix. Okay, that's all. So this is how we compute the density matrix. Okay. Yeah. Okay. So if these things are clear, this is just so what I want to say is this is exactly like a real random variable. So if you have done some probability, if you have a classical, if you have one single self-adjoint operator, which is like, then you can replace that operator by just this lambda 1 up to lambda n. This is like a real random variable. You get a probability distribution. You can talk about expectation variance. But when you have two of them, you cannot do that. Okay. Then there is something called measurement problem in quantum mechanics. This is a statement. This is not a theorem or something I can prove. This is an assumption. This is a postulate. Okay. So this is what is called measurement. So measurement, the axiom or something. Okay. This is not, we will not use this, but when you do quantum computation or something, measurement is a very important operation. Okay, you do something and you measure something. So you need to know this. Okay, what it means by measurement, you need to know. So this is what is called von Neumann collapse. Von Neumann is a great mathematician. Von Neumann collapse principle. Okay, collapse. Von Neumann collapse postulate or something. Okay. So if you have a random variable, if x is a random, so if you have so let's start with the probability space. Okay. If A phi is a quantum probability space, okay. And x is a random variable, x is in A and x equal to x star, a random variable. Okay. Then we know that, and of course, we assume that x is equal to summation lambda I EA. Okay. So we assume that x is equal to lambda I. Then we know that the probability of x equal to lambda I is just the phi of EA. Okay. Now, if you measure, if v or u or whoever, if you measure this random variable x, whatever it means by that, okay, if you measure it, then you to get the value of lambda I, the probability is that we know. But you suppose if you measure and you will get a value, you won't get probability, you will get a value. And if you find that if the measurement yields the value, okay, if the result of the measurement is lambda I, you can only get lambda 1 up to lambda n because that's the random variable. It can take values only up to lambda n. So it cannot take any other value in the real line. Suppose if it is lambda I, then the whole state collapses to this EI. The EI is the Eigen space corresponding to this lambda I. Then the state collapse to EI. What does it mean? It means that the new probabilities, new probability spaces, new quantum probability space is you can hit the probability space EI on both sides. You have algebra on a bigger space. You hit it by this projection. So what happens is you have CN, that is your state space or something. Now you have a projection. It collapses to the projection. Okay. So you have to hit the algebra with EI. And the new state is phi of, phi I, where phi I of any A, whatever that, A should be inside that, but I will write it like this, phi of EI, A, EI. Okay. That is how we, the new operator, the something in the orthogonal complement of EI does not matter, divided by phi of EI. This will be the new state. We should have phi. I mean, sorry, this is phi. This is not phi. This is
Isn't that EI star AEI or something?
EI is a self-adjoint operator projection, no?
Ah, okay, sorry.
So yeah, you want it positivity or something, you should have EI star or something, but it's a projection. So that's why. So this is our new state. Okay. So if you have a row, if rho is a density operator, if the state is given by density operator, given by rho, okay, the new rho is the new density operator. Is E rho, E divided by trace rho, trace E. Of course, trace, I mean, you get a measurement means the trace E should be greater than 0. Then only if it is 0, you will not get that lambda I, right? So it cannot be equal to 0. This is EI or something. This is the new density operator.
So it should be trace of the numerator.
Yeah, trace of the numerator.
But EI do EI, trace of EI divided by trace of
No, trace of EI. Sorry, correct. Sorry.
And trace of rho EI.
Yeah, correct. That's happening. Trace of, yeah, right. So you are right. The new density operator is EI. I mean, EI rho. It's fine. I mean, because it's a you are going to get it inside the trace, no? So it's okay. But you can write it if you want. We want it to be positive operator, so you better write it like this. Right. Oh. Divided by trace of EI rho EI. Correct. Yeah. Then only you will get 1, right? Not trace of EI. Yeah. Oops. What happened? What should we do? It's connected. The computer, the screen hasn't gone.
Yeah, sure.
It is good. Okay. So this is the measurement problem. Okay, it's clear, I think. Okay, so it will collapse to that new state. That's all. So this is the measurement problem. So okay, now let us discuss M2. So now example. So the simplest case we want to discuss and list out all the projections, list out all the states. Okay, when A equal to M2, C. Okay, this I want to leave it as an assignment. Some of it. Okay, maybe you. I mean, I will give the details. Maybe with all those details, you write it as an assignment. Okay, this is the assignment 1. Okay.
Should we submit the graduate analysis assignment?
Yeah, in your class, whatever I did, what did I do?
Like yesterday,
Yeah.
we gave an assignment. So that
Yeah.
also.
Yeah, that's also part of it. Yeah.
That's also part of assignment of this course.
Yeah. Whatever I do in that, you take it as that. Yeah. I mean, so you have an intersection, wherever you have intersection, you better do that. Okay. I don't remember what did I give.
Some function. You have to show if it's C1 space is better.
Huh?
Yeah.
C1 space.
Okay. If you wish, you can leave that. Okay. That's not important for you, but it's better you know that. Okay. That's more of analysis course than this course. I mean, the idea of this course is not that. So yeah, you can leave that. Okay. Other assignments you do. Okay. Okay. So in this, I want to say what are the events. So any state is given by. I mean, I want to list. So this is my algebra. M2C is the algebra. I want to list out all the projections. Okay, which I discussed in the first class itself. Okay. So any projection. So if you have E is a projection, E is in A is a projection, which is just a 2x2 matrix. Then E looks like this. Then I mean. E looks like this: half of 1 plus Z, 1 minus Z, X plus IY, X minus IY. Okay, X, Y, Z are in real. Okay, this is because since E is self-adjoint, E equal to E star. Okay, since E is self-adjoint, so that's why I have written the diagonal. So I mean that's why the off diagonals x plus iy and x minus iy, and the diagonals are real. So 1 plus, I have written it as 1 plus z and 1 minus z, and trace of, so E is a projection which is not equal to 0, which is not equal to 1. Okay, it's a, I mean, if it is E equal to 1, we know it's identity 1, 1, 0 means 0, 0. So it's not a trivial projection. It's a neither identity nor 0. Okay, and trace of E equal to 1, right? If it's a projection, the trace should be 1. Trace is actually sum of the eigenvalues. Okay, trace of any operator is just the sum of the eigenvalue. Trace does not depend on the eigen. I mean, with respect to what orthonormal basis you are writing the matrix, it's just the sum of the diagonal element. If you change that, that's because I have said this, no, trace of AB equal to trace of BA. So if you write it with respect to another orthonormal basis, it is just writing it like this with the unitary operator like this. But then you can take this U that side, and U star U will be 1 because of this. Anyway, we will see all this trace for a Hilbert space theory. So these things will be clear anyway later. So trace does not depend on the orthonormal basis. So trace of any, the projection has eigenvalue 1. So the trace is 1. Okay, 1 and 0, that is the eigenvalues of a projection. So 1 in the range of the projection and 0 in the other. So trace of E equal to 1. So because of that, E will look like that. Now determinant of E equal to, determinant of E should be 0 because it's a rank 1 projection. Okay, it's not, I mean, it's a rank 1 projection. So determinant of E equal to 0. So this implies, so 1 minus z square plus minus x square minus y square. So this implies x square plus y square plus z square equal to 1. Right? So so now you can see that anyway, any of these things, then, so
why the determinant 0?
because it's a singular matrix, no?
Okay.
It's not equal to 1, it's not invertible. Okay, it's a projection, one-dimensional projection. We are discussing, we are working with 2 dimension. So we are assuming it's not equal to 0 or 1. Okay, so determinant is 0. Okay. So what does it say? So for any such projection E, their axis x, y, z, such that x square plus y square plus z square equal to 1. That means x, y, z in the sphere in R3. Okay. So notation is S2, no, for R3. So S2 is a sphere. Okay. That is all those x square plus x, y, z in R3 such that x square plus y square is the surface of the sphere, not the open ball. This is sphere. Ball means less than or equal to 1. Okay. The sphere. So any such thing will have this. So on the other hand, if rho is a density matrix, rho in M2C is a density matrix, then also rho is greater than or equal to 0. Rho is a self-adjoint. Okay, then rho equal to rho star. Okay, and trace rho equal to 1. Okay, so it will look like that. But then then the determinant is trace rho equal to 1. I want to say that it comes from the ball. So you have the determinant. Determinant is less than or equal to 1, right? To compute the determinant of rho. So it's a density matrix. The determinant can be 0. No, determinant is. I want to say, what do I want to say? Huh?
Top right.
Here. What?
Oh,
That's not mine.
I don't know why it does.
The one short
No,
line
no,
on top of that window
This line
on the side wall.
here. There is this line. Oops.
Okay.
You have to hold it and drag it somewhere outside.
Here. This one. I don't know. Keep touching somewhere and oh, this is something else. What did I name? QP3, I think. Okay. This is the one. That was the earlier one. Okay. Yeah. So what is the determinant? Determinant should be, I don't remember why the tray. See, any point inside the sphere should give the trace of rho. Is the truth? That just means the determinant should be negative, right?
What do you want?
No, determinant will be positive.
Yeah.
Yeah, determinant will be positive. Rho is positive, so trace rho is greater than or equal to 0. Sorry, determinant should be positive. A positive matrix will have positive determinant, right? Yeah.
Yeah.
Determinant of rho is greater than 0, which implies x square plus y square plus z square is less than or equal to 1. Okay. Determinant is equal to 0 means x square plus y square plus z square equal to 1. So determinant rho should be greater than 0. So any density matrix rho is given by something determined by something in the ball. Okay. So the assignment is the following. It's not moving down. It's not moving down. It's moving up. What did I do? Okay. So these things we have done already. I mean, we have done. So I did the assignment is the following. Assignment is the following. So you define sigma 1 is a matrix. Sigma 1 is a matrix. Zero, 1, 1. I mean, these matrices are very important when you do quantum computation or something. Sigma 2 is this matrix. 0 minus I.
I think
What?
right and upper the 5
What is that?
options. I think the leftmost option is going to be
Leftmost option.
leftmost option of the upper right.
Okay. That what is it?
I think that's what is.
No, then something else is coming here. Now it's okay. Okay. This is what is sigma 2, sigma 1. This is just a matrix. Okay. These are all what are called polymatrices. Okay. And sigma.
You need to click that thing again.
Click thing. This.
The top left, the rightmost one.
But what did I do to get there?
I think that other hand is touching.
Other hand is touching.
Yeah.
Okay. I keep it out. Okay. Okay, this is just 1 minus 1, 0, 0. These are what are called polymatrices. Okay. Now, if we have A, I didn't touch anything.
I don't know how it is.
They're wasting a lot of time on this. Okay, keep my hands on that. Okay, so these are what are called polymatrices, okay, or spin matrices or something. Then if you have any A1, A2, A3 in R3, okay, you define sigma of A. You can define the polymatrices corresponding to sigma of A to be A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Okay. Then you can check that. I didn't even touch with the pen.
Whenever after touching that you are touching with the pen, it is going.
Yes.
Okay, sigma A equal to this. A3. Not even touching with my palm. So then the following thing is true. Sigma, I mean, this is just given by this. So this is the assignment, okay? A1 assignment is sigma of A times sigma of B, okay? It's equal to the inner product between, this is R2 inner product. This is also called as dot product or something, okay? Times 1 plus I times sigma A cross B, you know, the cross product, A cross B. Okay, this is the first assignment, okay? And E of A equal to half into 1 plus sigma of A, right? Half into 1 plus sigma of A. A is in the S1, S2, okay? And rho of A equal to half into 1 plus sigma of A. You will get the same matrix, whatever we have written there, okay? Where A is in and I don't know, the keyboard also changed to Tamil. I don't know. Oh, I didn't do anything. A is in the ball, okay, which is just all those norm A less than or equal to 1. Okay, it's the ball. Okay. Okay. Then I want to say that the trace of EA, you just compute this rho A, okay, which will be half, which is equal to half of, it's okay. If I touch there, it comes here. Half of the inner product with AB, okay, half of 1 plus the inner product with AB, okay. One plus inner product with AB. Okay. See, first you have to verify that E of A is a projection, okay, is a projection. See, let me recall, I mean, in this confusion, I didn't say properly what I said. If you have E is a projection, then E looks like this, that we have proved. You have to prove that when E is given by this, then it's a projection, which you can just check. E star is E and E square equal to E. You can just check, okay? And when rho is given by that, then rho is a density matrix. Trace rho equal to 1 and it's positive. And what else? That's all. So rho is self-adjoint. Okay, those things are clear. Then you can write it in terms of this poly matrix. Then you can write sigma A, EA, rho A in terms of poly matrix like this. Okay, one is the identity matrix. Okay, so we can write it like this. Then you can calculate the trace of rho EA, rho A. Okay, that is given by this. Okay.
Yeah. So this E of A, which we write,
yeah,
that is just the projection applied on A.
No, E of A is A is a number, A is a vector in the 3 dimensions. It's a sphere on the surface of the sphere.
Yes.
Corresponding to that, I have written it in this, it is precisely this E. XYZ, A equal to XYZ or something. Okay. E is not, E is a vector in R3, not in R2. E is a projection in R2. I'm just saying that the projection, all projection in R on C2, on every 2 cross 2 projection, 2 cross 2 matrices projection in M2C is actually given by the surface of the sphere. 3-dimensional, I mean, which is 2-dimensional, of course. Dimension of the sphere is 2. Okay, the surface of the sphere. Okay.
What is rho of A?
Rho of A, I have defined it here. No? See, this is the same thing. E of any A1, A2, A3 or X, Y, Z, whatever. It is just 1 minus A1 plus A3 half into 1 minus A3 A1 plus IA2 A1 minus IA2. Okay, which is also equal to half into 1 plus sigma of A. Or sigma of A I have defined. Okay, so we just verify all these things. That's all. Okay. Similarly for rho, it's the same thing.
So what is rho? Rho is the density vector.
Rho is the density matrix.
But
When rho A is inside the sphere, I mean, this is the surface of the sphere. When A is in the surface of the sphere, it gives projection. When it is a point inside the sphere, I mean, in the ball, okay, then it gives rise to density matrix. The surface of this is also a density matrix. A projection also gives rise to a density matrix. That has trace 1, it's positive, everything. Okay, so that's also a density matrix. Okay. And these are all one-dimensional projections.
For E, we need to verify, and we are defining rho to be that.
Yeah, rho to be. So rho also, rho, no, I have, see from rho also it follows the same thing, right?
I didn't understand why determinant of A is 0, but determinant of rho is greater than or equals to 0.
No, determinant of rho is positive.
Yeah.
E is a projection.
Yeah.
So determinant of E equal to 0. B is a projection, one-dimensional projection. So determinant of E is 0. Rho is positive, so determinant of rho is positive. Okay, and it can be 0 also. I mean, it's greater than or equal to 0. Okay, that's all. So what you have to check is the following: the probability of getting EA, probability of getting E when the state is rho. Rho is a state. The probability of E given rho is this. Okay. Now suppose A and B is 0. Suppose, I mean, for all, suppose A is such that the inner product with A, B is 0. So that means A equal to 0. Then you get the fair toss coin. Probability of EA equal to half. And see, EA, EB commutes. Okay. This is also another thing. I haven't given it in the right order, but whatever you have to verify, you just write. Okay. Doesn't matter. EA, EB equal to EB, EA implies A, B equal to minus A. Okay. So EA and EB are orthogonal projection. EA and minus A equal to 1, which you can check. Okay. This is equivalent to that. So every state will give rise to, I mean, if you have EA and E minus A, that is like you have 2 projection. That is like 2-point probability space. And you have a rho A, it will have, one of them will have the probability, whatever the probability I have given. It's really irritating. I will stop here and then I have given the probability of getting EA when the state is rho A is half plus 1 plus square, I mean, inner product AP. If we take minus A, it will be minus. It will be minus this. If you add them, it will be 1. Okay, so
then the last thing which you said, the commutativity of EA, EB, we are assuming A not equal to B.
yeah, A not equal to B. We are assuming.
Because I mean,
Yeah, you can assume
the
A equal to
implication
B.
would also, I mean,
A equal to B, what is the problem?
A equal, I mean,
A
equal to B also.
Oh, no, sorry, A equal to plus or minus A. Sorry, sorry. It has to be, yeah. A is plus or minus A. It is just plus or minus A.
Yeah.
Plus or minus A. B equal to plus or minus A. Yeah, that's all. Yeah. So when, say, okay, when A equal to 0, 0, 0, this gives rise to fair tossing coin. That means it is just you have any projection EA and E minus A, both will have probability half. Okay, so the whole thing vanished. Then 20 different file or what?
Scroll down.
Yeah, where is the right thing? What? It's the same file. It's showing something in not showing. When A equal to 0, sorry, when B equal to 0, this is B or A. What I have written? See, EA, trace of EA row B. Okay, this is B. A when B equal to 0, sorry, let me write B equal to 0. Pardon. When B equal to 0, then this B equal to 0, then the state row B okay, I will stop here.
Maybe use some other app next time.
No, I will just show it to you on the
You
board.
can write it on the board.
Yeah. I'm just saying that so you have the sphere, okay, all norm A equal to 1. Then all those E of A gives a projection, all those projections. Okay, and you have norm A less than or equal to 1. Okay, then row B, let it be. This gives all the state. Okay, then the probability of EA in the state row B, which is this trace, right? Okay, which is half times 1 plus A. And EA and E minus A. E minus A is nothing but 1 minus E. Okay, EA plus E minus A equal to 1. Okay. So if you just consider these two things, this is like a coin toss with probability. One of them is 1 plus this, another one is 1 minus this. Okay. So, and when AB equal to 0, I mean, when this is for all A, I mean, B is fixed here, B is a state. When B equal to 0, this is a fair cost. Okay. And B on the surface is all projection. Okay. On the surface, it gives a projection. That's also a state. Okay. It can be from the surface also. But they are all one-dimensional projection that correspond to what is called pure state. It comes from the vector space. Okay. It's like this. If you have something, I mean, if you have some vector, it's like this. No? This is also a state. Okay. So vector state. Okay, that's all. Okay, we will do it better next time. I will put it.
So when to submit this assignment?
Before midterm, I will give you many assignments. Before midterm, you will submit it.
So you make the assignment submission on